All right, take it away.
Okay. Hello again. My name is Masaru Nagaso. I'm currently working at the Nanyang Technological University in Singapore under Professor Tomping as a postdoc student. So today I will show you some of my former and current works, which is concerning on seismology, and probably them are not concerning about seismology. So at first, I will briefly explain my background because it's also not quite concerning about seismology. So my first project of research at Tokyo University of Science was about the computational fracture mechanism. So I was calculating these things on cluster, which was my first experience about using computational clusters. The problem was for solving some elastoplastic finite element method analysis for calculating the so-called intensity factor for calculating the way to propagate the crack. And at my master's degree, I totally changed my subject of the research. From here, I started to learn about the acoustics, but it was in the ocean and in the fish body, actually. So I was developing some visualization method using the acoustic probes to check the investigate the inside of the fish body. And I was also developing the code for FDTD, wave propagation modeling. And after finishing that, I moved to France for my PhD degree. I was studying on the modeling of wave propagation inside of the nuclear reactor because the coolant of the fourth generation nuclear reactor is totally opaque, and the visual optical method cannot be used. So we use the acoustic instrument inside of that, but there are some problems for using that because comes from the complexity of the coolant situation, especially the temperature heterogeneity was very strong. So this was the first time when I started to use SpecFEM. So we modelized the inside of the situation with some safety calculation. Then after we firstly applied the spectral elements method for simulating the wave propagation in such a complex medium like here. And here is my kind of side work, which I was doing during my PhD study with JVIS, which is a company in Vietnam run by my friend, one of my friends. And this is a project for developing a Python application for the researcher at Tohoku University currently, whose name is Naoya Fujiwara. This application was developed for making some comparative study between some method for network clustering. So we implemented the so-called map equation method and modularity, which is a more general way to calculate the cluster situation. And here is one of the others. This is also the work with JVIS and the collaborative work with the researcher Tokuda at the University of Tokyo. In his study, he wanted to calculate the so-called subject time of Alzheimer's disease, which is important to be calculated when for effective dosage of the medicines. So for this purpose, we applied a nonlinear mixed effect for fitting the curves with some function here, and using the 10, here it's 10. So 10 indicators of the situation of the disease. We try to fit and find the subject time in here, which is a shared parameter between all of those indicators of the disease. I implemented this with C++ and Python, and so that for the facility of the use. And here, yeah, it's again, it's a kind of a big change of the subject. So this was a collaborative work and industrial project with Recruit. This is a company Recruit company for staffing, which is the largest company in Japan for this kind of company. And JTB is a travel agency. So the purpose of this project was to classify the short text, which is sent from the customers, and based on this short text, the remote operator will find what the customer wants. So based on this short text, we made some a language model using a transformer LM, and for creating the feature vector of the words instead of using some general feature vector like TF-IDF or some kind of like that. And after that, we applied C2A for the classification task. Then, yeah, we implemented like this for this task. And here is one another machine learning project, which is a collaborative work again with Yamaha and Koito Seisakujo. This application is used for kind of mindstorming during the team meeting. So user have some specific word which they are interested in developing or selling some product, and this application will generate the model which can estimate and calculate out the most relevant words, which was learned from the. We actually used the Amazon review text, and we investigated some words which are related to some specific words, and the positive. We trained the model for finding some words which has positive connection with the specific target word. And from here, finally, we reached to my topics concerning of the seismology. So this was actually my postdoc work at I was studying at LMS CNRS. I was working on the CHEES project, which was a European Union Horizon 2020 research project. So in this project, some physical and numerical code was selected for optimizing the code for the use of exascale supercomputers. And of course, SpecFM 3D was selected among one of them. So, and the project investigated the code, and they found that SpecFM 3D has almost already optimized for the use of exascale supercomputers, except its I/O method. So, because there are some bottlenecks for I/O, what they are detected. So I made some work on performance improvements on I/O. And then the development of FWE workflow is a part of the objectives of this project. So we at first developed the GUI application for pre and post processing for making FWE calculation. Then we also developed the Python tool for allowing the user to do semi-automatic simulation setups. And at last, we want to give more simplicity for preparing the environment of the calculation. So we applied some containerization techniques for packing all the library and codes. So here is what we have done for performance improvements of SpecFM for exascale HPCs. At first, what was the problem on the I/O strategy that SpecFM 3D has been taken in the legacy code was to take the legacy end-to-end strategy, which means the same number of MPI processes, all of the MPI processes output each output data. So that means the number of the output files will be easily enormous when we once try to start the big computation. And this number can easily hit the limit on the HPC system, limit of the file numbers on the HPC systems. So this is reducing the number of the output file is one of the objectives. And also the I/O bandwidth is limited. So even if the number of the output file is reduced, once again, the I/O bottleneck exists for this problem. So we applied the asynchronous I/O method for SpecFM 3D. And my contributions is at first I added the parallel HDF file output format support to SpecFM. And then I implemented I/O server, which means MPI process dedicated only on file input and output. And then I added some output function for XDMF file, which allow to direct visualization with, for example, ParaView. So when the size of the calculation become larger, the post-processing time is will be longer, and which can be even longer than the calculation. So we need to some way to mitigate this process. So XDMF5 plus HDF5 visualization was applied for this purpose. And in the develop branch of the main public SpecFM 3D is already included. It has already included my updates as those options. So you can use try to use this function. And here's the explanation about how the I/O server works. So in the blue rectangle part is what I added to the legacy code. So here is a computation node which calculates the normal stuff, like and the I/O nodes do only the I/O I/O processes. And in the legacy computation flow, as you can see, C is the computation time, and I is the I/O time, and W is the waiting time for synchronizing the processes. Then this I can be very large if the calculation is hitting the I/O bandwidth limitation. Oh, sorry. And when we use the I/O server, this I time can be transported to the I/O server processes like this, and we can shrink the total WR time like this. And here is analysis with Intel VTune that I carried out. In the legacy code and the HDF5 corrective without I/O server, as you can see, there are some waiting times. And when we use the I/O server, this waiting time can only shown in the I/O server process, which is actually waiting for finishing the all calculations after finishing the I/O processes. And this graph shows the speed up rate for some I/O heavy I/O tasks. So, like like writing out every 3D data at each iteration. So with this setup, even the legacy code and the legacy method can be far from the ideal speed up lines like this in the blue. Then we found that the HDF5 corrective I/O is the worst case. In the library, they are doing some inefficient. It seems that inefficient work is done during the I/O. Then in the green line is the speed up ratio with I/O servers. So we can see that with I/O server strategy performs very well compared with the other method. And here is the explanation about the workflow package development. So we developed some pre-post processing tools like PySpecFM, which is a Python library for making semi-auto configuration of file and directories. So user can prepare only one text file with some parameters, and PySpecFM will convert this set of file to the directories and parameter files for running SpecFM and MeshFM as well. Then we've also developed the GUI application and customized the RASIF application for allowing the easy data preparation and the quality check as well. And the SpecFM FW is developed by mainly Vadim Monteillet, which implements the optimization method with LBFGS, and Axisem coupling is already there. Then Laplacian iterative smoothing on GPU and CPU is implemented as well. And the correlation matrix on VT, VS and rho parameter can be imposed with this. And finally, we shipped all of these code as one single Docker image or singularity image. Here is some example of the GUI. So user can visualize the downloaded events and configure the boundary of the simulation domain, like here. And the preparation of the reference signal can be done in here. And the user can check the quality of data by checking the counter of the plotted data, like which indicates like the time shift and the amplitude abnormal amplitudes. And this is the example of the axisem coupling forward simulation for Japanese island. So those are the things that I've done with at the LMA, CNRS. Then from here, I would like to explain about what I'm now doing. After finishing my postdoc work at this LMR, I started my postdoc at here, Nanyang Technological University for developing a seismic travel time tomography library, which uses the equinary equation for the core solver. This is our open source project for calculating the travel time tomography for slowness and azimuthal anisotropy. And one of the main objectives is to make a large scale calculation. In this library, local and teleseismic events with absolute and common receiver and common source double difference travel times are supported now. So here is a list of objectives. So one of the objectives is to make a calculation large and at the same time, we want to make the calculation at small and local laptops with high accuracy and efficiency. And good usability is one of the important aspects for us. For that, we applied the equinary equation based solver. And we used the spherical coordinates with higher order stencil scheme. And we applied the multi-layer MPI parallelization for scaling up the problem size. And HDF5 collective I/O. Here's some example of input files. We only need 3 input files for making a calculation. One is the source receiver file, which is a data set of seismic event and the receiving time at the stations. And the second one is the initial model file, which can be easily prepared as a HDF5 file format. This library also supports the ASCII format, but we highly recommend to use HDF5 for the computational efficiency. And the third one is a parameter file, which can be prepared as a YAML file format, which is like this. We selected the HDF5 plus XDM format as my SpecFM contributions for simplify the post-processings. Here, maybe we can briefly go this part because everyone knows this. Here is the objective function, which just calculates the difference of the travel time between the synthetic and the observed one. And here is the equinary equation calculated on Tn, which is a synthetic travel time field. And then this is an explanation on the spherical coordinate system, which we only consider as azimuthal anisotropy like this. Then here is a gradient of objective function and adjoint field. We applied the multi-grid model parameterization as a smoothing method, which is studied by Pin. And we also implemented the iterative smoothing method with inverse Laplacian operator as well. And here is some other techniques which we applied. We are now using multiplicative factorization technique, which can avoid the singularity at the source point. And we also applied the third order WNO-based Lux-Friedrich fast sweeping method. Here is some technical things. We applied 3 layers parallelization for fast sweeping method. The first layer is here. We can divide the data set for several simultaneous run groups, and each group can be run simultaneously. Then we can also do the domain decomposition for mitigating the memory size limit on one single computational node. Then the third one is a parallelization on the sweeping plane. So by using the Cuthil-Maki node ordering, all the nodes on one single plane can be computed simultaneously. So this makes the calculation much faster than the legacy node ordering. And I also implemented some optimized routine with SIMD optimization. And I also tried to CUDA backporting. And here is a comparison of speed-up ratio. With SIMD optimization with AVX and FMA, we observed almost 8 times faster than this baseline over time. Then here is a CUDA implementation. It looks very good, but sometimes CUDA don't work well, depending on the size of the grid, because the Cuthil-Maki node ordering, the number of the nodes at the corner is very small, and if this kind of a plane is if this small plane is domestic on entire planes, the parallelization with CUDA is cannot calculate very efficiently. And here is a performance test that I made on Fugaku, and we could verify that the code is well scaling with 3 different sizes of grid, forward grid simulations. And here is a brief introduction of the application. We applied the data at the California plus Nevada region with almost 40,000 seismic events with 950,000 P-wave travel time records. And the number of the station is 3,300. And the grid points is more than 1 million, like this. So we are now investigating this result and making some publication from this result. here is the comparison from between the former and the current result, and we verified some similarity on the slowness, calculated slowness field and anisotropy field like this. So that's the end of my presentation. Tomo ATT is now developed as open source code, so you can check the code by accessing this repository. But currently, this repository is in private mode because we are now preparing an update, and which will be released at the AGU of the end of this year. So after that, I would like to ask to use the library for getting the users, and hopefully we want to make some user communities like SpecM is now has already been built up. So thank you very much for listening to my presentation.
I'm going to stop the recording.